Ladies and gentlemen, and thank you for coming today. Now, we would like to present our new device for this century that is called direct formic acid fuel cell or DFAFC.
Let's begin in this graph. So you can see that everybody needs energy. For example, most of people use mobile phone to communicate. Why do we use formic acid, hydrogen peroxide in fuel cell system? Formic acid and hydrogen peroxide are liquids, so they can use in deep water that has high pressure. For example, marine application submit warning system because of simplicity of storage and recharging.
A fuel cell is an electrochemical energy conversion device. A fuel cell converts the chemical energy from a fuel into electricity through a chemical reaction. A single fuel cell consists of an anode and a cathode, with electrolyte in between. Hydrogen molecules add to the anode, then react to the catalyst and split into proton and electron. The electrolyte allows the proton to pass through the cathode. However, electrons cannot pass through the cathode. Instead, they are directed through to the external circuit, creating electrical current. Oxygen molecules interact the cathode. Here, the oxygen and the proton combine with an electron, producing water and heat. Individual fuel cells placed in a series to perform a fuel cell stack, which is used in a system to power vehicle or provide stationary power in home or building.
Parts of a fuel cell. The anode, the negative pole of the fuel cell, has several jobs. It conducts the electrons that are freed from the hydrogen molecules so that they can be used in an external circuit. It has channels etched into it that disperse the hydrogen gas equally over the surface of the catalyst. Next, the cathode, the positive pole of the fuel cells, has channels etched into it that distribute the oxygen to the surface of the catalyst. It also conducts the electron back from the external circuit to the catalyst, where they can then combine with the hydrogen ions and oxygen to form water. The electrolyte is the proton exchange membrane. This specially thin materials, which look something like ordinary kitchen plastic wrap, only conducts positively charged ions. The catalyst is a special material that facilitates the reaction of oxygen and hydrogen. It is usually made of platinum nanoparticles very thinly coated onto carbon paper.
Okay, so I'm gonna tell you about how it works. Okay, so in this picture, the formic acid will go to the anode side, and then it will split off into hydrogen ion, electron, and carbon dioxide. And then the hydrogen ion will go through the electrolyte, but the electron will go to the external circuit, to make electrical current. So we can use the electrical appearance over there. And then we use the hydrogen peroxide to combine it with hydrogen ion and electron to make water and come out.
Hydrogen peroxide must not be exported directly to the sun and keep it 15 to 13 degrees Celsius. So we contain it in the open gas bottle. Storage of formic acid is much easier and safer than that of hydrogen because it doesn't need to be done at high pressure and a low temperature. As formic acid is a liquid at standard temperature and pressure. Catalyst for DFAFC. Platinum rubidium commercial catalyst is the most active discovered to date for formic acid oxidation. But because of a limited natural resources, platinum cannot be used in the large-scale production of fuel cell, and alternative materials are needed.
Okay, let's see the result under discussion. Please take a look at the first figure on the left side of this page. It is a cell polarization. These are 10% formic acid and 15.5% hydrogen peroxide at room temperature. It is an IV gap. A bimetallic metal anode catalyst were tested. 20% platinum, 10% tin shows lower performance for oxidation than 20% platinum and rubidium that are commercial catalysts, but it is still better than the already prepared catalyst. Now let's see the second one on the right side of the display. This one obtained from the first one. It is an PI graph. It is found that the 20% platinum and 10% tin exhibits 30% lower electrocatalytic activity than the commercial catalyst. And now this figure shows the cell performance of platinum and tin at a different ratio, such as 20 by 10, 15 by 15, and 10 by 20% as an anode catalyst. The 15% platinum and 15% tin carbon gives maximum power. And now, as shown in the figures, 15% platinum and 15% tin catalyst show 17% lower performance towards than the commercial catalyst. Meanwhile, it shows about 40% cheaper price.
And then this is our DFAFC model. In each one, it contains a stack of fuel cell. In each fuel cell, it contains about 6 individual cells of fuel cell. And in each individual cell, it contains cathode, anode, electrolyte, and catalyst between them. And then we have the 2 containers of hydrogen peroxide and formic acid.
Okay, now I will reveal all of you about the advantage points of our model. The first, it cannot drink into explode because it is the liquid, it's not the gas like hydrogen and oxygen. The second, we don't have to stimulate the reaction all the time like using hydrogen and oxygen. The third, it can be used in high pressure like my friend says, in the deep water like marine application. And the last one, carbon dioxide as the project can be used for making dry ice. That's the economic benefit. Thank you for attention.
จบการนำเสนอหัวข้อแรก